Okay, so like I said, this will be discussing the chemistry of combustion, arson, explosives, and even larger things like larger weapons, nuclear weapons, fusion weapons. And so it's just anything related to burning or exploding, what chemical evidence is left behind. So behind drugs, combustion products or evidence is the second most common forensic analysis. So we need to know a little bit about combustion basics, what makes a fire, what makes this transition from combustion to an explosion, and then detonation, and then the basics of designing of like weapons of mass destruction. So we're going to go from the simplest little match all the way up to the largest thing that we can blow up. This would be a fusion nuclear weapon. And it's still even the, well, not the nuclear stuff, but all of the explosives and the fires are related to the fire triangle. So we need three things for a fire, and really the fourth is important too, mixing. So we need fire, heat, and oxygen, or some sort of oxidant, but oxygen's most common. In all of our fires that we deal with on a daily basis, there's oxygen in the atmosphere. So we'll discuss the ratios of fuel to oxygen that are optimal. But you need also heat. You need that activation energy. So we're chemists. We understand the kinetics. You need to get over the activation energy before the reaction can go. If it's an exothermic reaction, then that helps its neighbors overcome that activation energy. And so you might have a spontaneous process that is a maintained fire, like it keeps going, it propagates. This idea of mixing is important, and let me show you this video of what happens when it mixes. So here's let's see, shrink it down, move it over. So this is a house fire. It's a mock-up just to demonstrate. So this is
these instructions. 1, turn off the heat. 2.
All right. It's like a public service announcement, short video.
If your pan catches fire, don't panic. Just follow these instructions. 1, turn off the heat. 2, run a cloth under a tap and drain it out. 3, cover the pan and then wait until it's cooled right down. Don't try and move the pan.
So what did they do? They put a moist towel over the pan. So we had a fire actually going. So in order to stop the fire, we needed to either get rid of the oxidant or get rid of the fuel, okay, or stop the mixing. And so this does a couple of things. One, turning the heat off is actually taking away the fuel because the vapor is what burns. The oil vapor is what burns. And so there's this interface of the oxygen with the vapor that is burning above the pan. If you turn the heat and the vapor pressure of the oil starts to drop, then it won't sustain a fire anymore. You're also removing the heat for the activation energy, and then the towel acts as a barrier to keep oxygen away. So you're separating the mixing. So it's doing all of those things. But we typically think of fighting the heat with water. Most of the fire extinguishing things, they come in with water hoses. And so she says, don't throw water on the oil. Now, do you know, in organic, did we ever use oil baths in organic? Well, probably because they're pretty dangerous. But if you want to get something above 100 C, you can use an oil bath. Okay, so if you're using just a boiling water bath, you're fixed at 100 C because that's the boiling point of water. But if you want to go up to 200 C, you can put it in an oil bath because oil can go much higher than 100 C. You get up into the 300s, oil can get up there, but it starts to char and decompose and smoke. So if you put oil in a pan and it's getting up above 300 C, you'll see it start to smoke and it'll stink up the room, okay? But you're getting a lot of combustible products off the top of that oil because it's too hot. It's way hotter than the water's boiling point. So what do you think happens if you throw water in that oil at 200, 300 C? The water immediately flashes to steam. Well, if the water has gone into the oil as a water droplet and flashes to steam, anytime you go from a liquid to a gas, the volume increases roughly 1,000 times, okay? So one little droplet of water can expand to something 1,000 times larger. And that's like a little mini explosion. And so it vaporizes that oil and sprays it into the room. And now you've got mixing, you've got fuel, you've got oxygen, you've got temperature. So it does this. So they just threw water onto that pan.
You don't throw water over the fire.
That's amazing. Yeah.
The effects can be devastating.
Because she's done this, her face is all burned because she's threw water on a pan of oil. Yeah. So that was a public service announcement to kind of shock you into saying, don't ever throw water on hot oil, because you just throw a cup of water on there thinking it's going to put out the fire, and the whole room is now a big ball of fire. They did this a few years ago in the parking lot of Walmart. They had a little city safety thing with the fire department, the police department, the kids could climb on the trucks and everything like that. And they had a turkey fryer. And they had the hot grease over the propane. They built a little shed, a little wooden shed, kind of like this. And they, with a long pole, just dunked a turkey down into that hot grease with all the ice crystals and everything on this frozen turkey, and it boom, and it just blew that little room up. Yeah. So it's pretty scary. So I just can't imagine how slowly. Has anybody fried a turkey? How slow do you have to lower that into the oil to keep it from doing this? I don't know, but I'm too afraid to do it. I mean, yeah. So I just can't imagine that the heat would get all the way into the middle of the bird, but I know people like it. Any experience? No. Oh, okay. You kind of raised your hand. So. Yeah. Okay. Very good. Now, just to make a point, let me move this video out. Get up there somewhere. No, I must have made it full screen. Didn't try again. Exit full screen. I just can't get it. Here we go. Let's do that. Okay, so then I don't know if you've noticed, but on our YouTube channel, the Forensic Chem at Sam YouTube channel, there's a lot of playlists. And some of the honors contracts in the past, I had students go through and set these playlists up. Turn this on. Yeah. And so we have these playlists curated by some former students, and they're all on the different topics of the course. So if you scroll down, there's the greatest hits, but there's alternative light sources, guns and GSR, and here's arson and combustion. And it's a pretty cool playlist. And they've got videos on the fire triangle and demonstrations and things like that. So these aren't required, but they're just added interesting things. So like if you wanted to kind of get some more understanding about some of the topics that we talk about in class, go check out the channel and look at those playlists, because they're topical based on the different lectures. And so hopefully you'll enjoy that. And we can watch some of these too. Okay. And so in terms of firefighting, we can take away the heat with water mist. If the fire's already going and you've got your equipment on and you're at a safe distance, you can spray water on it. Even on an oil fire, you hit it with enough water and keep everything else wet, you'll eventually extinguish the fire. But by yourself in a little pan, like what you saw in that video, don't do that. CO2 powders, they have a chemical effect. They will again exclude the oxygen from the fuel, and it's sort of taking the oxidant away and preventing mixing. And then foam, so like a fuel fire, you see foam trucks at airports. If there's a crash or a leak or something, they'll come out there, and if the fuel catches fire, they'll spray foam on it, and that's a physical effect. It takes away the heat and keeps things from mixing.
What's done in fire?
A lot of times it's CO2 powders or like sodium bicarbonate, something that produces CO2 when it decomposes. And so this powder that's blown out there is something that decomposes into CO2, which is, again, a combustion product. So it's a stable, even in a fire, it's stable because it's the product of combustion. You would need an extremely hot fire to pull the oxygen away from the carbon. It would have to be something electrical or some other kind of heat source that's way hotter than that thermolysis of CO2. So CO2 is a very stable compound, so it's not going to combust, and it will, like if you throw a powder on there and it decomposes into CO2, once again, we have this expansive effect. So it pushes the atmosphere back and pushes oxygen out of the way, okay? But again, if it's pushing oxygen out of the way, you don't necessarily want to do that in an enclosed space, right? So sometimes firefighting, that's why a lot of firefighters, just because of smoke inhalation, but also, any of those kinds of effects, they want to have their own air supply so that they can breathe. Yeah. And then halogens, the carbon halogen bond is really strong. And so it takes away the heat if you're decomposing the halogens. So if you spray like carbon tetrachloride on the fire, which is bad in terms of your breathing because it produces hydrochloric acid, but it steals so much heat from the flame that the fire will eventually die out. And so that's what I saw this in an old pharmacy museum at Texas Tech. They had a 1800s pharmacy, and on the corner were these fire extinguisher bombs, and these were glass balls of carbon tetrachloride that you throw at the base of the fire. So if you got the trash can catches fire, you throw this bomb in there, and it soaks everything in carbon tetrachloride and puts the fire out. It seems crazy, and we know from this train derailment in East Palestine that these chlorinated compounds produce some nasty air pollutants and so on. So it's not the preferred way to put out a fire. That's why we don't see these today, like in the corner of the classroom. We have these much more human-friendly fire extinguishers. Now let's talk about combustion. Most of the experience that we have is with slow-burning fires, campfires, things like that, s'mores night, but then there's this transition. If you have the oxidant that's put into the material, like in terms of gunpowder, they'll take carbon, which is the fuel, and they'll put in nitrates and sulfates and things like that, things that have oxygen, things that are oxidants. And when the primer sets that powder off, the oxygen's already in the material. And so that's why it'll even burn underwater. Okay, so the oxygen's already in there, and it will burn vigorously, which is what we call deflagration. So that word right there at the top, it says burning, flame, deflagration. So that might be a new word for you there. And there's a video on the playlist called The Difference Between Deflagration and Detonation. This person has made some gun cotton where they react regular old cotton balls with nitric acid and nitrated the cotton. So it's nitrocellulose. Maybe you've heard of nitrocellulose. We still use that in our artillery shells because it deflagrates. If it were to detonate, it might shatter the cannon or the shell or whatever. So we want something that burns and produces a lot of gas in a controlled manner. And nitrocellulose is very easy to control in that manner. If you've got a good chemist that produces it well, you can generate gas at a controlled rate. And those are called propellants. So, my cousin is a gunnery sergeant in the National Guard, and so he always tells me about the cannon lines, and like if they wanted to go a certain distance, they put the shell in, and then they look like marshmallows. They're little satchels or cotton sacks of gun cotton, and they put 1 or 2 or 3 in there, depending on how far they want the shell to go. And then they pick the angle. So there's all kinds of little factors. They put the shell in, put three bags of gun cotton in, and they pick a particular angle, and it'll put the shell right where they want it to go. It's that accurate. So gun cotton I've seen it in the lab. I've seen, chemists do demonstrations with it. You see it on those videos, but it really is a useful thing. Like it's manufactured for very precise artillery. Then if it's burning fast and you confine it, it might transition into a detonation. And the way we determine the detonation or deflagration is the speed of the burn. So if it's subsonic, then it's a burning or a deflagration, and we would call that a propellant or a gas producer. If it goes supersonic, then it's the little thing doesn't line up. The little explosion or detonation, it turns into a detonation. Yeah, so look at it from the side, you can see. And so that's really this shock wave. And now it's kind of strange to think about what is this idea of the shock wave or speed of burn. It's very simple to conceptualize if you're burning a match, right? It's how fast the match burns down the wood. And it's obviously slower than the speed of sound. I mean, you can count seconds before it gets to your fingers, and you throw it in the fire or shake it out. But in an explosive, that transition of energy goes faster than the speed of sound. Now that's bizarre to me, because how does it transmit from one point to another faster than the speed of sound? Light has to be involved in some way. So it's almost like a radiation front of energy that blasts through. It might be infrared from the fire. So when that infrared goes through the material and it's enough to essentially build up into maybe even visible region, build up to where it breaks all of the covalent bonds in the material, you have a detonation. So think of a combustible substance. If I were to send an energy wave through that substance instantaneously and break all the covalent bonds, all I have are free atoms at a really dense spot. And now they can rearrange at will. The bonds are already broken. And so if there's oxygen right there next to carbon, snap, they go right into CO2. If there's two nitrogens together, snap, they make nitrogen gas. So they're making all these gaseous products instantaneously. And that's when you have an explosion. So an explosion happens in milliseconds. Hollywood explosions are not explosions, they're deflagrations. You see the big billowing flames that come out of the building, that's a deflagration. It's produced a gas that's burning as it goes. A detonation is like an artillery shell or maybe you've seen videos of these improvised explosive devices. You don't see any flame, you just see the shock wave, bam, and then destruction. Then you might see a flame later, but that initial explosion, that's the actual detonation. So combustion, the chemistry of it, this particular combustion of wood. Wood is a carbohydrate, and so that word carbohydrate is actually in the empirical formula, carbon and water, carbohydrate. So all of cellulose, all sugars, all starches have the same empirical formula, CH2O. They're all carbohydrates, carbon and hydrogen. So these names actually mean something. You've heard of hydrocarbons, that's just hydrogen and carbon. If you put oxygen on those, then in the oil and gas industry, they call those oxygenates. So they're hydrocarbons that have been oxygenated. So there's alcohols, ethers, acids, and so on. They're mostly hydrocarbons, but they have some oxygen because they've partially oxidized in nature. But combustion of wood, you can just look at that, this generic carbohydrate formula, CH2O, plus oxygen produces 1 mole of CO2 and a mole of water. And so then let's analyze the flame a little bit. Down here at the bottom, you've got thermolysis, where it's breaking some of the covalent bonds in the wood. The wood actually doesn't burn, the wood decomposes. I know that's a technical point, but if the wood burned, the flame would run down the wood really quickly. But the wood just cooks and decomposes, and it's the gases that burn. You can kind of see the flame isn't really on the wood. It's surrounding the wood. And the same with candles. The wax melts, it goes up the wick, and you can look at the candle. If you look closely, like I do, I love to look at things like this. I'm like, that is so cool. It doesn't look like the flame is really touching the wick. It's the decomposed oils and waxes that are breaking apart, and little ethyl groups are coming off, and little propyl groups are coming off. And so all those tiny molecules are burning in the gas phase above the wood or above the wick. And that's why the wick, it may turn black from the carbon residue from the combustion or the decomposition, but it doesn't burn very fast. Like if it gets out towards the hot part of the flame, then it'll start to burn a little bit of the cotton wick. But for the most part, it decomposes first. Then the blue flame is the redox reactions, and mostly that's from hydroxyl radical. So when we're making water, we make the OH. As this molecule gets from the excited electronic state down to the ground electronic state, it's emitting blue light. And so most of the blue light comes from this hydroxyl radical. And then some of the residual carbon is still hot, and so it's producing black body radiation. So you can actually measure the temperature of the flame by measuring the visible light that comes off of the hot carbon soot, and use the Planck distribution to sort of measure the heat of that flame. And if you have very little, like if you have complicated molecules, long waxes and so on, you produce a lot of carbon soot. And in fact, you can see that if the wick is too long on a candle, it will produce a lot of black soot, and it'll get, it'll rise and land on stuff. It'll get on the little glass container sometimes. But smaller molecules like methanol, they don't produce any soot at all because it's just a single carbon atom. And sometimes you can't even see the flame. And there's, some of the Formula One race cars, they use methanol as fuel and you can't even see the flame. So you see the driver, like in the pits, jump out of the car and is dancing around because he's on fire, but you can't tell. And so the pit crews know, they start spraying them down with a human safe fire extinguisher. But he's on fire and you cannot tell. He just looks like he's going nuts. And so I saw some videos in my feed recently because I was looking at some of this stuff and I was like, oh, that's terrifying. So anyway, you might see some of those. If you start watching these playlists, that'll be in your For You, and you'll start seeing people on fire and all kinds of things. So fair warning. And so this is the QSAR equation that we developed in PChem 2. I went through the CRC and typed in the enthalpy of combustion for 900 compounds. I was bored. And I ran a linear regression on the molecular formula. So the number of carbon atoms, hydrogen atoms, nitrogen, oxygen, and this is the equation that I got. So I got coefficients for each of the letters. So whatever A is, the number of carbons, I multiply that number by 426.9. And B, I multiply that number by 88.2. Nitrogen is kind of, I probably should just exclude it from the model because its p-value was too high. But, it just basically I have a 1. Because reduced nitrogen, in this molecule training set, I had some amines and I had some nitros. Both have nitrogen. And they kind of work against each other. So that's why the nitrogen effect cancels out. Since the amines behave different than the nitro groups. And then the oxygen number times a negative 163.5. So that's kind of an important point. So this is an equation that can give me my combustion enthalpy in terms of kilojoules per mole. And so all I need to know is the molecular formula, which is pretty cool. So you give me the molecular formula, I can tell how much heat is generated per mole of combustion of that material. So I think it's a useful little equation, and it matches literature pretty well. The perfect match would be, if I'm plotting my model versus literature, would be a slope of 1. Essentially, they give the same number. And if there was no scatter in the data, an R squared of 1, obviously, and I got an R squared of 0.99. So that's pretty cool. It goes all the way up to C70. So all of your waxes and oils are in here. They would fit on this model really well. The reason they're scattered down here is as I can't tell the difference between, say, ethanol and dimethyl ether. So those would have different formulas, different structures. An alcohol has the oxygen bonded to a hydrogen and to 1 carbon, whereas a dimethyl ether has an oxygen bonded to 2 carbons, and that would give a slightly different heat signature. But for my model, I don't have that in my model. So that's why there's a little scatter that my model doesn't catch. So I think it's a useful equation. This tells us then how much we get per molar mass. You see, most of the hydrocarbons kind of converge on this line around 40. So we get roughly 40 kilojoules per gram. And so a lot of practical applications just use everything in terms of mass. So for your fire inspection, the fire marshal will come in and he'll count up the sprinklers in this room. We got 4. See those little round circles? If this room gets hot enough, the sprinklers will pop down through those circles, and the little valve that's keeping the sprinkler closed is a little piece of plastic. And if it's hot enough in this room, that plastic melts and the valve pops open and it sprays water and puts out the fire. Now that's going to pump only so many gallons of water into this room a minute, and the fire marshal's thinking of the amount of kilojoules that can put out, and he looks at the combustible loading in the room. And so if we had lots of cardboard boxes stacked in here and so on, he would say you've got too much combustible load in that room for the fire suppression system. So what that would mean was that this room, a fire in this room would not be contained. It would burn through the door and burn through the walls. So he wants to make sure that if every room has a manageable combustible load, then the fire suppression system will contain the fire to that room. And they deal in mass and in kilojoules. So they come through and they kind of estimate how much burnable stuff they have by gram, or by kilogram. I always got dinged at Pantex. The guy would come through quite often because it's a plant that makes explosives, right? So they're very fire conscious. And I had so much paper. I had all my files and everything. And he would come in and he'd say, you've got 2 filing cabinets full of paper, and this room can't handle that kind of combustible load. And I would say, but they gave me 2 cabinets. And he said, well, you can't use one of those cabinet drawers. Okay. And say, okay, fine, because I didn't want to get in trouble. Now, what about all of these compounds down here at the bottom? Those are oxygenates. So these are acids, alcohols, and so on. And this right here should convince you that blending ethanol into our gas is a stupid idea, because we're taking away, we're putting in so many gallons, and yet we're getting less energy per molecule, and even the QSPR, we're putting in here a negative for every oxygen in our molecular formula. We're losing kilojoules. Why is that so? Well, because this is the fuel we're talking about, and if it's already partially oxidized, we're not going to get as much energy out of it. So we want the least oxidized fuel in our tank if we're burning it to get energy. And so anyway, chemistry doesn't lie. It's just not a good idea to put already oxidized fuel in our tanks. We must be doing it for some other reason, but it's not because it's more efficient. Okay. So let's look at the fire marshal kind of calculations in terms of mass of fuel versus mass of the oxidant. So Q in this case is the heat generated. It comes from the mass of fuel, and it's fast. In thermo and in PChem 2, we talk about adiabatic versus isothermal processes. Adiabatic situation would be where there's no heat flow through the walls of the container. And so this occurs in a couple of different ways. One is if it's fast and there's no time for heat to flow out. And then 2, it's a simplifying assumption. So if you assume, like worst case scenario, if we burn this desk in this room, the worst case scenario for our fire suppression system is if all that heat stays in here. All right, so this would be the worst case. If we lose heat through the windows or something like that, then the fire suppression system has an easier time of removing the heat. So adiabatic conditions would be the worst case scenario. And so they use that as the basis of their calculation. There's huge forces, so we want to calculate the max moles of gas, the highest temperature, and then we look at these stoichiometric ratios. So again, this is on a mass basis. So we're typically interested in, as chemists, in moles, right? We deal in moles of this and moles of that. But in practical situations, most people deal in masses. So you have the mass of fuel divided by the mass of oxygen for your system, right? This is the actual system. And then you can look up, if you're a fireman, you probably have tables, you can look up the stoichiometric ratio for the actual fuel that you're estimating. So if they're looking at paper, they're going to use cellulose, they're going to use, wood and paper's STE value. So let's calculate an STE of methane in air. So here's methane reacting with oxygen to make CO2 and water. So like I said, we typically think in moles as chemists, but what are the mass numbers? So we got to convert all of these to mass. And in a fire situation, we're not talking about pure oxygen. We're talking about air. So we need to know the mass of air in the denominator, not just oxygen. So how many moles of air will produce 2 moles of O2? So here's our atmospheric composition. So in terms of a liter of atmosphere, it's 0.21 liters of oxygen. In terms of moles, you've got 1 mole of the atmosphere, you've got 0.21 moles of oxygen. So that would be our conversion. So from 2, if we need 2 moles of oxygen, we get 0.209 moles of oxygen per mole of air. So that would be that many moles of air. Well, let's calculate the molar mass of air. So 1 mole of air is going to be that coefficient for the nitrogen, right, times the nitrogen's molar mass, and then the coefficient of oxygen times oxygen's molar mass, and the coefficient of argon times argon's molar mass. And that gets us down to the third significant figure. CO2 is down in the 4th significant figure. Water fluctuates between 1 and 5%. So a lot of these calculations are done in dry air. I mean, humid air is just going to make things better. So this would be the worst case scenario on a dry day. So think of Southern California and all years previous to this one. So they've got a huge rainstorm and floods and so on. And so this would be the amount of moles we need. That would require 277 grams of air. But now we know also the molar mass of air. So you probably want to, I will put that on the little equation sheet, and I'll put the composition of all of this. And so all these equations will be on the equation sheet, including the molar mass of air. And so this is our ratio. We needed 2 moles of, or we needed 1 mole of methane. So here's the molar mass of methane. And then we needed the amount of oxygen. Stoichiometric for that would be in 277 grams of air. So when we do this ratio, it's about 6%. So about 6% fuel would be the perfect situation. Okay, and that's when you really have an explosive hazard. So naturally, the question would be, it says yes, you need to do these calculations. Okay, so then the calculation would be, or that we may be interested in, is would a 5 liter per minute gas leak reach an explosive concentration overnight? So you got a natural gas heater or something like that. You put something in the closet that's located in, and you bump one of the hoses. It's an old hose and tiny little hairline crack, and you don't hear it, but 5 liters per minute is leaking out, which is a moderate leak. It's not really small, but it's not huge either. Okay. Now, you would never know that if it was straight methane because it's odorless. So they put this thiol in there, methane thiol, that's real stinky. I mean, it's bad news. And, the idea is hopefully it smells so bad that it will drive you out of the house before there's an explosive hazard. We got our heater replaced, and the guy was bleeding the lines. And I said, "You're bleeding the lines until you smell it?" And he goes, "No, I'm bleeding the lines till you smell it." And I was like, "Oh, you should have told me because I smelled it a long time ago." Yeah, and I mean, it was bad. And I said, "I'm nervous now." And he goes, "Oh, no." He said, "It had to be a lot worse than this before you're at 6% and blow you up." Yeah. So here's, 8 hours. Well, we got to know, in terms of 5 liters per minute, we got to get out of hours and into minutes. So 60 minutes per hour. It's 5 liters per minute. So now we know how many liters we have. We've got to convert using the ideal gas law from liters to moles of methane. So using the ideal gas law. So V equals nRT over P. And you assume 1 atmosphere. Okay. So that would be the volume per mole. Okay, and then you've got the molar mass of methane. So you're out of moles of methane. and then convert from grams to kilograms, because we're going to probably estimate that we're going to have kilograms, and we do 1.57 kilograms of methane. So that's how much methane we have. What about the actual amount of oxygen? Well, we've got to estimate the size of the house. So this is just a hand waving now. It's like, what kind of house do we have? We have a 5,000 square foot house. Do we have a 2,000 square foot house? Let's pick a modest house, 2,000 square feet. It's not tiny, but it's comfortable. And let's pick 8-foot ceilings. So we're trying to get a volume here. We got 2,000 square feet. That's the footprint. Now let's raise that up 8 feet. We're not going to take into account the attic, because the attics are typically sealed, covered. There's very little communication from the house area to the attic, but for efficiency's sake. So we'll just take the 8-foot box times 2,000 square feet. So that's how many feet we have. Need to look up the conversion of liters to feet, cubic feet. And now we got liters. And now we can do that again, ideal gas law. Same number in terms of the molar volume. And then grams of air per mole, and then again to kilograms. So 536 kilograms of air in that house. So then we take the ratio, and we get 0.00293 kilograms of methane per kilogram of air. That's our system number. It's less than 6%, right? And so this phi, this is the reason I wanted to calculate phi. So we have our system on top and our stoichiometric amount on bottom. If that were 1, we would have the perfect stoichiometric amount. And so this is kind of a percentage of the stoichiometric amount that you have. We have about 5% of the stoichiometric amount. We have 0.05. That's way far from 1. When this is 1, you have an explosive situation. When it's far away from 1, you're safe. I mean, it's still nasty in there. It stinks like the deal. It's probably still something that would make you have a headache if you were breathing that methane, a little bit from oxygen deprivation, but it's not going to blow up. And so this phi is the basis for all of our explosivity calculations. This is what we call too lean. There's not enough fuel. Now, if we had waited a really long time, let's say we had this gas leak, it's in an abandoned house, and it goes way past the stoichiometric amount. Let's say it was 1.95. So it would be all the way on the other side. It would be too rich to explode. And that's a possibility too. You have way too much fuel, not enough oxygen, it's not going to explode. It's dangerous though, because somewhere between the rich fuel area and the lean fuel area is the Goldilocks zone. So you don't want any combustion sources near the windows or the doors of this house, because that's where you're going to pass through the explosive area. And so you want to be very careful opening those doors. You don't ring the doorbell with a little spark. Yeah, so it's a very, anytime you're too rich, it's dangerous, not in the rich area, but between the rich area and the lean area. You're going to pass through an area which is perfect. So this is what we call this LEL and UEL. And you'll see this listed on the MSDS sheet or the SDS sheet sometimes. It'll give you the lower and upper explosivity limits. So when phi is equal to 1, that's when it's explosive. They typically say at 0.25 that it's safe. It's not. It's somewhere between the explosive and safe level. There's some risk of a large fire, okay? But below 0.25, it won't sustain combustion. So it's not even a fire risk. Now that's what we assumed was perfect mixing. But methane's lighter than air. So it's going to collect around the ceiling. And so this calculation with perfect mixing, the methane's going to rise to the top of the room. And so it might be actually too rich at the very ceiling, but there might be a flammable zone or an explosive zone just down below the ceiling, and then a lean area down here where it's not strong enough. So, all gas leaks are bad. I'll just say that. Yeah. And then with the way we do our doors, even if we have an 8-foot ceiling, the door has a little bit of a, it's down below the ceiling. And so that rich area up there can reach the explosive limit up above. It won't blow the house to smithereens, but it could create an incredible fire inside one room of the house. Now in explosives, we have a thing called oxygen balance, because if we're trying to make an energetic material, that's the general term for explosives and propellants is energetic materials. We've put oxygen in the actual molecule, and we're not burning it with exterior oxygen. We're trying to burn it with the oxygen inside the molecule. So this is the oxygen balance inside the molecule that we've built in. So this is a different kind of calculation. So this is the generic reaction for carbon, hydrogen, and nitrogen. Notice the molecule itself doesn't react with oxygen. It just decomposes and burns within itself. And so again, from the number of carbons, we form CO2. From the number of hydrogens, we form water. And it's B/2 because it takes 2 hydrogens to make a water. And then the nitrogen, we're making nitrogen gas. That's the most stable form of nitrogen. So once again, worst case scenario, if it's able to make dinitrogen, that's a gas which will expand the most and give us the largest push in an explosion. If it doesn't quite form nitrogen gas, then it will give less push. But this would be the best or worst case scenario in a bad explosion. And then we have all of these terms that deal with the oxygen, like the amount of oxygen that went into the CO2. Let's see, there's 2 of those that went into the CO2. There's one of those oxygens, the B/2, went into the water. So those oxygens are missing. And so then we have the amount of oxygen minus that amount divided by 2 to make O2. So if we have excess oxygen in an explosive, it will actually produce O2 gas. And then that O2 gas after the explosion can burn other things. So if we have a positive oxygen balance in a molecule, it has more oxygen than it needs to burn all the organic components in that molecule, and then the oxygen can burn other things. You could still have a molecule that will detonate with a negative oxygen balance, meaning one that doesn't have enough oxygen, because it just gives enough energy from the carbon, the water, and the nitrogen to explode. The one nitroglycerin has a positive oxygen balance. So we have, in this case, 9 moles of oxygen. It needs 6 for the CO2. It needs 2.5 for the water. And it has a little bit left over. So if we subtract 6 from 9, we have 3. If we subtract 2.5, we have 9. And so we have 0.25 left over for moles of oxygen. It's that D/2 after it subtracts all those other things. And so it has a positive oxygen balance. So that 0.4%, that plus 4%. TNT, on the other hand, which is, again, a very familiar explosive. Hopefully you've heard of TNT. It has it's a low by 74%, and yet it's still a decent explosive. But it's not the most powerful explosive. There are other more powerful explosives that have a higher oxygen balance than TNT. Let's talk about the heat flow in a fire. So this is an example of a candle melting. So you have the solid warming up. So as the heat goes into the wax, it warms it up first. So it's warming, then it starts to melt the wax. And look at that. You know this from just your everyday experience. There's a melting point, and the solid liquid mixture at equilibrium will stay at that temperature. So whatever the melting point of the wax is, that's the temperature of the top of the candle, because the wax and the liquid are at the same temperature. They're at the melting point. As more heat flows in, it doesn't raise the temperature of the liquid because it's in contact with the solid. And so just more solid will melt. And that's why you leave a candle out too long, it'll melt the whole thing. because it's just pumping heat into that liquid, and that liquid is just melting the solid, and it's just getting deeper and deeper and deeper. Okay, so it's fixed at that melting point. When you run out of solid, then you're kind of at a risky situation, because now the liquid can heat up. So then the liquid heats up, and if it's something that can vaporize, it will boil, and then you'll be at the boiling point of the liquid until all the liquid's gone, and then you'll heat the gas. So that's the normal behavior of a substance. If a candle wax gets hot, you start to heat the liquid, it'll start to smoke and decompose and then produce combustible gases. So that's why they say don't leave candles unattended, because the solid will melt completely, then the liquid will start to decompose and produce combustible gases, then the flame will jump down on the surface and start to propagate on the surface of that hot candle. You have more flame, more heat, more decomposition. Eventually it'll work its way out of control. Still burns slowly, but it's a dangerous situation. Most of the time, though, that liquid flows up the wick and decomposes and burns, and we've already talked about that. Now, this boiling area is really important for arson investigation, because if you're stupid enough to try to burn your house down with a gallon of gasoline, and you just pour it in the carpet in the living room and light it on fire, it'll catch your house on fire and it'll burn it down. But what will happen is that boiling liquid will protect this middle part of soaked carpet, and that carpet right there will be fixed at the boiling point. And so they look for this donut pattern, and this is the physical evidence that's left behind. So the carpet here, this thermolysis front, is decomposing, and it's the decomposition products of those polymer fibers that are actually burning, and the heat is decomposing more carpet, and it'll go down to the base floor material, whatever that is. If it's wood, it'll start to char the wood. And then this front area, this is again protected by the boiling point of the fuel. And so sometimes if for whatever reason it's put out before the place completely gets involved, then there'll be fuel here and fuel there, and you will have an ironclad case of arson. Somebody dumped fuel in the carpet, and you were able to even tell what kind of fuel it was. It was diesel, it was gasoline or something like that. So that's a dumb way to do arson. Okay, so then we've talked about pyrolysis. It's the decomposition of the material, and as arson can leave those distinct patterns. I don't want to get too much into arson investigation because that's a later lecture, but typically the number one principle, I'll emphasize this today and then as well. Number one principle: heat rises. So if that fuel is burning in the middle of the living room, the carpet may be fine and the ceiling catches on fire. So the heat is rising and it's catching the stuff. And so typically if it's by a wall, you'll see a char pattern that is just a V, and it's pointing right to the source of the fire. Like it started right here. You come in the room, the ceiling's all black, you sprayed everything with water, so you destroyed a lot of evidence. But you can still see this V that goes right down to the electrical plug or whatever it was. Or in the kitchen, it's a coffee maker. You see the cabinets are destroyed above the coffee maker. The ceiling is destroyed. And you come in and you're like, over here it's not burnt, over there it's charred, and the V just leads right to the source of the fire. And that's if you can get it out before the whole building burns down. And so if they respond fast enough, a lot of times they can find the source. So this deflagration to detonation is typically called a DDT. It's a deflagration to detonation transition, and it's where this pressure builds up and it turns into a shock wave. If it's just a flame like a candle, there's no pressure buildup. If it's a propellant, you've got it in a confined space and it builds pressure to do something. Bullets are not the only thing we use propellants for. We use them for driving nails into concrete. You can buy these little what are they called? I forget the name. It's a little thing that you can buy at Home Depot that comes with these little 22 blanks. And you put a nail in there, you put a blank in there, and you point it to your 2x4 above a concrete pad, and you punch go, and that 22 shell drives the nail through the wood and into the concrete. And that's a use of propellants. That's not like a firearm. Now it sounds like a firearm because it's 22 shell. It's a rimfire 22 shell with no bullet in it. It's got a little crimp top. Okay. And then if you take that pressure buildup and put it in a confined space where it runs through a material like an explosive, that shock wave can cause this deflagration to detonation transition. So there's different types of explosives. There's low and high explosives. So low explosives are typically those with the lower oxygen balance. So they produce, less heat, less shock wave, less force. And then there's these types right here. So I want you to focus on this line right here. So there's different kinds of sensitivity for explosives. So the sensitivity is how sensitive it is to detonation. That's probably one of the largest safety issues, is understanding explosive sensitivity. And there's different things that can set off an explosive. There's spark, which is what it sounds like. Spark is a spark. Shock is not a spark. Shock is mechanical. So when we talk about shock-sensitive explosives like nitroglycerin, it's not talking about what we would call getting shocked like static electricity. That's a spark. It's getting hit by something, getting shot by a bullet or hit by a hammer or in a car wreck. So if you're driving down the road with a bunch of artillery shells in the back and somebody opens up on you with a 50 caliber weapon, you don't want that explosive to be shock sensitive. Because if one of those 50 cal bullets hits that artillery shell, it could blow you to smithereens if it's shock sensitive. And so they've made shock insensitive explosives that can be shot with a 50 caliber weapon and not go off. So that's a pretty amazing safety feat. Heat. So if you get in a fire and explosives in a hot situation, how long will it take before it cooks off and blows up? And then friction. Some things, kind of like match heads, you scrape that match head along and that friction can cause it to start the reaction. So this is different detonators that operate on some of these different techniques. So here's one that's flame initiated. So you burn a fuse and you've got these low explosives here in the orange region. And typically the low explosives are primaries. And that's the first thing that sets off a detonation. So it's the one that transitions from burning to detonation. Then you'll have the primary or booster explosives in this green, and then you have the output explosive, the one that's actually giving you the energy that you want. So these detonators are really quite technical. So this fuse can start it off. You can have these low voltage electric matches, and these little things right here. Has anybody ever done hobby rocketry? You make your little rockets and you go to the store like Hobby Lobby and you buy the rocket kit and you buy the little motor and you buy these little fuses, they call them. They're electric matches. And you can put a 9-volt battery on there and run 9 volts through this and it'll burst into flames. And it sets off the motor and takes off. So you do 3, 2, 1, and the rocket goes. So you can buy these little electric matches, but you can't buy this part. Okay? Not easily. Unless you have an explosive license, you can't buy that part. Now, when you get into really safe explosives and really precise explosives, you get into these kinds of exploding bridge wire or slapper type. These would be military or government use type blasting caps. Maybe they use them in mining. I'm not sure, but but for sure on military weapons, they have these type of exploding bridge wire, and they need a really high voltage. Okay. If you take this and put it inside a larger charge, then that explosive detonator can detonate a larger charge. So here are the chemicals that we're talking about, the different explosives. These are primaries and low explosives. So these are the more sensitive explosives. We'll see this one a lot, this lead stiffenate. So ammo primers. It's shock sensitive, which makes sense because we want to hit it with a firing pin. And so that's a shock initiation. You have a firing pin pulled back by a spring, and your trigger releases it, and it crunches that little primary and catches that lead stiffenate on fire. It doesn't detonate, but it burns, and the flame goes into the gunpowder inside the cartridge. And then the gunpowder starts to burn, and it builds pressure, and then the bullet is released from the front of the cartridge, and it shoves it through a tube. Okay. The longer the barrel, the more pressure is generated because it builds up faster than the bullet can exit. If you have a short barrel, it comes out and there's still lots of fuel to burn, so that you can see a lot of bigger flame from a shorter barrel. And we see that too. When I shoot a pistol, a lot of flame. When I shoot a rifle, same charge. You know, I have ammo, like I've got 22 rifles and 22 pistols. So you shoot a little 22 out of a pistol, you get a lot of flame. You shoot it out of a rifle, most of it's burned by the time the bullet exits. And so you see very little flame come out of a rifle. And then these others, mercury fulminate, lead azide, and so on. These are, I guess, different common primaries. Then you have nitroglycerin and nitrocellulose. And then this one here, the most common, I guess, commercial production detonator uses PETN. And I'll put here easy to, quote, sniff with instruments. So in a situation where we're trying to detect explosives, even though this isn't the main charge, it's the thing we're smelling with our instruments. It's penterithrotol, that tetranitrate. So it's a more of that explosive charge, it's probably the most volatile substance. And so we have our sniffer, stick it in someone's luggage or whatever, or in a situation where we think it's a bomb, you know, we sniff for it and we're like, yeah, we smell the detonator, it's probably a bomb. So we pull that back out and figure out how to deal with it. Here's the main charges. These are the things that give the most explosive power. And there's different classes, and I want you to know the classes, like nitramines. So these are functional groups that we don't really cover in other organic classes. Nitramines. So look at this. This is an amine right here, and a nitro hooked to it. So they're kind of combined two words, nitramines. And then we have nitroaromatics. So we have the nitro group stuck on an aromatic ring. And then let me go back to the previous page. These are nitrocellulose. These are nitro. So nitrocellulose, it's kind of a, I admit that it's different, difficult. This is an NO3 group. Okay, and it's sort of bonded. It's like a nitrate ester bonded to this organic molecule that's not aromatic, and then on the aromatic it's just an NO2. So. Oh, I should say this. We'll call these nitrates. I'm sorry. It's called nitrocellulose, but these are nitrates. Okay. So let me mark through that right there. organic nitrates. And then this one has, the more nitro groups you put on an organic ring or an aromatic ring, the more explosive power you're going to have. You have these the tetramethylene, tetranitramine. You've got 4 of those or 3 of those. Those are given these, abbreviations, HMX and RDX. I know that RDX stood for Research and Development Explosive. And it's not important, but I'm just kind of giving you where these names came from. And the British came up with HMX, and we don't know what the HMX really was. It's not hexamethylene because there's 4 of them as tetra. And so we just, for lack of a better name, we called it Her Majesty's explosive because Queen Elizabeth, and it was a British explosive. So that's how I remember HMX. Yeah. And then TNT, trinitrotoluene. You know toluene, right? It's a benzene with a methyl group on it. And so you got 3 nitros on it. Picric acid is trinitrophenol. And then TATB, this is the least, and it's on the homework, I think, sensitive explosive. And I will say most safe. You can shoot that with a 50 caliber weapon and it won't go off. You actually need an explosive to set this off. So they'll make a detonator, they'll have a booster, which is one of these other explosives, and then that explosive will set off the TATP. Now it gives you quite a bit of power, but it's very safe. And so unless you shoot the detonator, it's not going to go off. Now just last bit of information is, where's the evidence come from? In this particular case, you have the detonator, the booster, the main charge. So the detonator builds up this shock wave that goes through the material. It comes out of here like this and propagates through the material. So I'm just drawing kind of the contour lines of how that explosive shock wave goes out into the material. Notice I've drawn 4 lines, and look how fast it moves from point 1 to 2 to 3 to 4 into the main charge. So going straight on, that shock wave's going fast. Look at how slow it turns the corner. You see how slow it turns the corner? This is called corner turning for that shock wave. And this corner turning is slow, and low energy. Why is that important from a forensic standpoint? Because that's where your evidence is going to be. There will be always unburned explosive. Even in a nuclear detonation, there will be unburned explosive. But the nuclear detonation will get rid of it. That's one case where you won't have any chemical explosive left at the site of the device. But anything short of a nuclear detonation, you will have unburned explosives. So you will be able to find, you have the potential of finding evidence to say the main charge was HMX or the main charge was TATB or what have you. There's going to be some evidence left behind because nothing ever burns perfectly. This is why I was so shocked that they set those tankers on fire, because fire's not complete. It doesn't completely destroy stuff. It evaporates and spreads stuff and burns some stuff. And so they produced a lot of pollution with that fire. Now, maybe that was the better of the other options. I never knew what the other options were. They knew that they were building pressure in some of those rail cars, that they would have an explosion and would spread that stuff all over the community in an explosion of the tank, where the tank just ruptures and blows that material everywhere. So in their evaluation of risk, they said burning it would send the pollution higher in the air and create a smaller mess, I guess. I don't know. I wasn't in on the talks, but that was, in my mind, a controversial decision. So this main charge can slam 2 subcritical masses of fissionable material together and make a critical mass, where then you have a runaway chain reaction, a nuclear chain reaction. And so that's how a fission bomb works. And then if you put something that can fuse in between those things, that fission reaction can create enough heat and pressure to cause fusion to take place. So we know how to make fusion energy. We just can't control it. So when people talk about fusion energy, we can burn hydrogen. We can burn fissionable materials, lithium and other things, but we don't know how to control it yet. So that's, that's on the future. That's on the horizon in terms of our energy production. Now, if you want to knock things down or break things, we need to think about how much pressure is produced in the environment after the explosion. The shattering ability is called Brisance, and that's this first sharp, when you have a detonation, you have this sharp pressure wave right here. And that's the shattering effect. And then if you were able to have like a vigorous burning afterwards to produce a slower pressure wave, then you could have overpressure for a longer period of time, and that pushes things. pH pushes things. And you only need a few ounces per square inch of overpressure to knock things over. Like if we had just a few ounces of overpressure in this whole room, those windows would be gone, and maybe even part of the wall. Okay, so it's just the problem is maintaining it long enough for this item to give. And so that's what they do. They put blast enhanced powders in these explosives that burn in air. And that's what they call vacuum bombs. This is a news release from a year ago that says Russia now admits the use of vacuum bombs in Ukraine. And a vacuum bomb, they call it a vacuum because there's a splash effect where after that overpressure, the atmosphere splashes back, and that's a vacuum, and that can knock things over too. So you have an overpressure and an underpressure. So you create a splash in the atmosphere, and one way to do that is with metal powder. So they have an explosive, they'll have metal powder, and they'll disperse that metal powder into the atmosphere, and it's hot, and then it burns in oxygen when it reaches the stoichiometric amount. And if you look at the combustion enthalpy for the hydrocarbons, the metals are 2 or 3 times more. So if you take zinc or aluminum powder and disperse it in the atmosphere and it burns, you'll create an enormous overpressure wave. It won't really be a shock wave. It'll be a push wave. It'll be it'll still look like a shock. But it'll knock things over more effectively. That's what they call blast enhanced explosives. They had these even back in Vietnam where they would knock out the trees for a landing zone for a helicopter. Okay. And so they're still using them today. That's what some of these, when you hear a vacuum bomb or enhanced explosives, that's what they're talking about, is these are things that push buildings over and destroy lots of structures. Okay. Depressing place to end, but that's the science behind combustion and some of the science behind explosives. Okay. A lot of material today. Thank you for sticking with me.